started. Okay, so you have, yeah, get me really quiet today. You have an assignment due today, tomorrow. Any questions or problems? Okay, I want to emphasize for the CAS problem, if you get stuck on test 7, as some of you have, just go look at the Canvas, the actual write-up for the problem in Canvas. It has an additional test case that you probably are overlooking. So I've seen that a few times where people misunderstood something that's revealed by that test case. And I've also seen students that, because the examples that I give always stop on day 3, they conclude that every example, the rumor spreading should stop on day 3. But no, the rumor spreading continues until it can't spread anymore. Just a coincidence that it was day 3 for the examples, because they were small examples. Okay. All right, so we've been talking about shortest paths algorithms, and we looked at 2 last time. One that was completely general, as long as there's no, we make the usual assumption, and then negative cycles, and one that only worked on DAGs. And this one sits in the middle. It's called Dijkstra's algorithm, because it's an efficient algorithm that works as long as there are no negative edges. Now it turns out that it works even when there are negative edges. It's just that it's no longer very efficient. It's no longer, I shouldn't say very efficient. It could become extremely inefficient in the worst case. So that's why we block negative edges for Dijkstra's algorithm. Another thing I want to point out is the J is silent. So don't say Dijkstra's algorithm or something like that. Dijkstra was he died a few years ago, but he was a prominent Dutch computer scientist that sort of made his name originally being, he developed a compiler for Algol 60, which is sort of a language that a lot of other languages in the last century grew from. Okay, so what I've got on the right is breadth first search, which we've seen before. On the left is Dijkstra's algorithm. Now, I like to present Dijkstra's algorithm in a different way than the book does, because I like to emphasize the similarity with breadth first search. And that causes a problem when I ask questions like on a quiz that says, in what order does Dijkstra's algorithm visit vertices or stuff like that? I have to be careful that I mean the version on the slides, not the version from the book. They're the same algorithm, but they might do things slightly different. So typically this is what I mean when I talk about Dijkstra's algorithm. So they both take a graph and a starting point. They both initialize the distance in previous arrays. They both create a data structure and add the starting vertex to it. The difference here is breadth first search uses a queue, and Dijkstra's algorithm uses a priority queue. They both have this same loop. They both remove something from the queue. In the case of breadth first search, it removes something from the front of the queue, removes a vertex from the front of the queue. In Dijkstra's algorithm, it removes the thing with the smallest weight from the queue. They both iterate through the edges, looking for edges. So in each case, you've got a vertex U. You're trying to find all edges that go from U to V. And in this case, we care about the weight. So this just means find all edges from U to V of weight W. And they both have this, if a condition is met, they do these manipulations. This is our familiar update operation that we saw last time. Okay, so we'll see this in action. I wanted to point out the obvious parallelisms between the two algorithms. So let's see how it works in action. Here I have a directed graph. It's not a DAG because I've put that cycle back in with CF and G. And we can run through an animation and see how Dijkstra's algorithm works. Now, I spent a couple hours yesterday converting my PowerPoint slides over into Google Slides. And then I realized this morning I didn't go back and make sure I hadn't made any mistakes. So I wouldn't be surprised if there were a few glitches in the animation here. So you can help me out and point out any mistakes. So first thing the algorithm does is initialize the distance array in the previous array, just like breadth first search does. So there's our starting point. Well, we're starting at vertex A in this case, trying to find the shortest path to all of the vertices. And A initially, or A has a distance of 0 from itself. Okay. Then we create a priority queue of size V. So I tell it the maximum size it's going to have. And then I stick S, which in this case is A, into the priority queue with a weight of 0. So in the priority queue, the vertices go into the priority queue, but they have a weight. And that weight is their the best known distance, the current best known distance of that vertex from the root. And of course, with A, we know exactly what it is. So I'm going to color vertices purple when they're on the queue. So we're ready to enter this loop. We've got the queue initialized, and that picture over there is synchronizing with this. So if the queue's not empty, we pull, we do this delete min. Now what's a delete min operation going to do on this priority queue? How's delete min? What is it? What am I asking for?
Yeah. The min element?
I want the element with the minimum weight. So in this case, there's only one element. If there was more than one, I'd be looking for the one with the smallest weight. Yeah?
I can remember if two things have the same weight, it's just based upon which one was put in the first, like a one, two, or does it not matter?
It doesn't matter. If there's a tie, it doesn't matter. Like usually, I'll typically prefer alphabetical order just to make it definite. But yeah, that's sort of an irrelevant decision if the weights are the same. So each time through the loop, we're going to pull a vertex off. And I'm going to color it yellow up there. So when I color a vertex yellow, it means that we definitely know the shortest path from A to that vertex. Okay? Now why is that? How do we know that there's not a path shorter than 0 to A? Yeah?
Well, because Dijkstra's doesn't deal with negative edges, and you can't have less than 0.
Okay, so there are no negative edges. We're assuming there's no negative edges. Now, if there were negative edges, it's conceivable if you take that edge from A to E and turn it around the other way, so it goes from E to A, and give it a weight of, say, -6 instead of 6, then there'd be a path of length 0, right? To A, from A to itself. You go A to B to F to E and back to A, and that would be a weight -2. Well, that's a negative cycle, so let's make it negative, make that edge -3. Anyway, with negative edges, there could be shorter paths from the vertex to from the start vertex to itself. But since we're ruling out negative edges, there's no way we can find a shorter way from A to itself. So a vertex comes off, we color it yellow, and then we have to consider all the edges out. In this case, there's 3 edges out, and I'm going to color them green as we're considering them. Okay, so for that green edge, we do this. If the distance to V is greater than the distance to U plus W. So someone tell me, why does that make sense? Why is that something that we're looking at? Why are we asking that question? Yeah?
It's kind of like if we take this path, is that going to be shorter than the current shortest path?
Right. Distance has the length of the shortest path discovered so far. So what we're saying is, if the shortest path we know currently is bigger than what you would get if you went from A to U and then follow the edge from U to V. In this case, the distance to U is A, so the distance to U would be 0 plus 2. So this says there's a path of length 2 to B, and that's one we know so far is infinite, so we need to pay attention. So we'll update that. So we execute this, and it's going to update the data structure. And what's going to change about the data structure there? What change will appear in the priority queue in the previous array and in the distance array. Okay.
B's previous will be A, and then distance will be 2.
Okay, so look, pay attention to B. Previous should be 2. Distance, previous should be A, distance should be 2. And it ought to show up here on the program.
Yeah.
Okay. So I call it purple now, just to remember the things that are purple are on the priority queue. So I call the things that are purple the fringe. The things that are yellow are fixed. We found the right solution. Now, why don't we color B yellow at this point? Why is it up in the air? Why? I mean, you can look at the graph and see there's not a shorter way to get to B. But, yeah.
There's an edge from A that we haven't explored yet.
Right, there's an edge out of A we haven't explored yet. And maybe,
There's 2 edges there.
turn that edge around from F to B and give that edge a weight of -3. And suddenly there's a shorter path there to B. So we don't know that yet. Even if it weren't negative, I just put a negative edge in, I realize, but even if it weren't negative, you can set up a situation. There may be a shorter path from A to B via some circuitous. We just don't know yet. Okay? We continue along. We're looking at now the edge from A to E, and that's better than the infinity we know about right now, so we update. And the same thing for that edge from A to F. We update. So we explore all the edges out, and if we find a better way to get to a vertex, we use it. So now our fringe is always sitting on the priority queue, and it's illustrated up there. Okay, so what's going to happen next? Yeah.
We'll pop B off the priority queue and examine it.
Okay, so we're going to end up back up here. We're going to take the minimum element off the priority queue, which will be that B. And at that point, I'm going to color it yellow, meaning we're not going to find a shorter way to get to B at this point. Now, that's important to understand. Why are we not going to find a shorter way to get to B? Yeah?
Because all the possible edges, the weights are stored in the priority queue. You just pull the spot is always.
Okay. So the only other ways to get to B are going to be via these fringe elements, and they're all further away, or at least as far away from A as B was. And since there are no negative edges, we're not going to find a shorter path. So this is where the negative edge property is really used. But we're not going to have to consider changing B again. Now what's going to happen?
We'll look at its edges.
Now B is our, U in this case is B. So now we're going to look at the edges one at a time out of B. Okay? Is that a better path to C than the one we knew about? Yeah, the one we know right now is infinite, so this is going to be one of link 3, and C's parent will be B. There it goes. Then we consider that edge out of B, and that's an improvement, right? Currently we know a way to get to F of weight 4, but if we go A to B to F, that's weight 3. So we're going to pass this test. We're going to take the known distance to B, which is 2, add 1 for the edge, and that becomes F's new value. So F is going to change now. What will this become? That'll become B. That'll become 3. What else will change?
F will be replacing the priority queue with F3.
Right, we're going to update the weight on the priority queue. So you see all that change. And now our fringe is here. Okay, and we just continue in this fashion. So we're, again, doing update operations, but we're doing them in a controlled fashion. Rather than updating everything sort of at random and then doing it over and over again, we're starting from the start vertex and flowing out. Okay, we pull the minimum off, which could be either C or F. I'll take C. We explore the edges out. So we explore that edge. That's a better way to D. We haven't ever found a way to D, so that'll be weight 4. And there we explored G. We haven't found a way to it either, so it goes on as a weight of 5. Okay, so here's our fringe, everything we've explored out to. And we're looking for edges out. So what'll happen next? Right. We'll pull F out and make it yellow. And now we've got to consider some edges. So we consider that edge. Now I could have told you before, without even looking, that that edge is not going to be fruitful. Because it's from a yellow vertex to a yellow vertex. And as long as no negative edges, that's not going to be a shorter way to get to C. The algorithm considers it, but it's guaranteed to reject it because that's always going to be false, as long as there are no negative edges. If there are negative edges, then things that have come off the priority queue goes back on the priority queue, and our efficiency goes out the window. But we keep our negative edges away, so that's not going to update anything. We're going to consider the edge from F to E. Is that of interest? Okay, that's a better way to E. That's 5 instead of the 6 we have right now. So we update E to be B and 5. Okay, there's my first typo. That should be a 5. Oh, no, that's right. I was looking at the edge from A to F. Right. Should be 4. A to B to F to E is the path we found. So 4 is correct. And then we're done with that. Back to the top. We look for the smallest, either D or E. I'll take D. It has only one edge out to H. That's never been seen, so that's a better way. We update it. Put it on the priority queue. That's all the edges it has. Okay, we're gonna, I'm confused as where I am.
Pulling E off.
Oh, we're pulling E off the queue. It becomes yellow. There are no edges out. So we're gonna come down here and pull G off. Explore one of its edges up to F. That's not going to work out. That's the only edge. Okay, that looks like I skipped the edge from G to H in the animation. Finally, there's nothing left to pull out, but yeah, I didn't skip it. So that edge turns out not to be an improvement. Then we pull H out, and it has no edges. And we're done. No more edges, and the queue is empty, so we're done. Okay, so that's Dijkstra's algorithm. Hopefully you see how similar it is to that first search. Any questions I could answer about that? All right, let's analyze it. We should be getting better at this because we've done it for breadth first search and we've done it for depth first search. And the analysis is going to be very similar. What's the complexity of the initialization block up there? Right. That's just O of E. What about creating the priority? Excuse me. I'm not going to speculate because I haven't said where the, what the priority queue is, how it's represented even. So I'm just going to say, we'll just let that be symbolic. So it's whatever the cost of creating the priority queue. That's the complexity of that. Adding the key to the priority queue. It's whatever the cost of an insertion is. That loop test. How many times will we execute it? V times. So it's V times whatever the cost of testing whether the priority queue is empty. So I won't speculate, I'll just leave that symbolic. How many times do we do a delete man operation? Okay. V times. If you think about it, when I took something off the queue, I colored it yellow in the graph. Because I asserted it would never go back on the queue. So as long as there are no negative edges, we can say this is executed at most V times. If there are negative edges, that's where the analysis becomes worse. So you're going to do V delete operations, whatever they cost. Enumerating the edges. Over the life of the tau algorithm, we got to find all the edges, and that's just going to depend on what kind of data structure we're using.
inserting the queue.
Or change, do a decrease key.
Okay? I guess by update, I guess I should have said, I think this is the test I wanted, that I think about. So this test is executed E times, that's a constant time test, once per edge. And then we do these updates here, doing this stuff here. It's dominated by edges. So each edge could potentially lead to an insertion into the priority queue. So we're just counting operations, and we're saying, I don't know what the cost of an insert operation is, but whatever it is, we do it at most E times. That depends on our data structure. This depends on the priority queue and so on. So let's add them all up. Now, how can we simplify this? Let's make some reasonable assumptions. Yeah?
Are we doing an adjacency list or adjacency matrix? So that would give us enum.
Right. So yeah, we can't replace enum until we get to a point where I choose one representation of that. What's a reasonable assumption we can make about any priority queue? What ought to be the fastest operation?
Delete.
No, that's login.
Delete, insert.
Empty?
Yeah, is empty seems like we ought to be able to make that constant time. Just by keeping a count. So, and to create a priority queue of length v, remember when you create it, you give it the initial length. If it involves initializing an array of length v, that might take v time. So if we make those two reasonable assumptions, it simplifies to that. So v times the cost of deletion, e times the cost of insertion, and then whatever the cost of enumeration is. So that's where we're going to say a matrix. And so that becomes O of v times delete plus O of e insert plus O of v squared. Now, a lot of you may be sitting there thinking, when I say priority queue, I mean binary heap.
No.
But in fact, I mean there are various data structures you could invent to implement a priority queue. So if you're trying to minimize this total sum, what would you wish for?
You mean
Yeah.
like in the Fibonacci heap? Or?
Well, it doesn't even have to be that. I'm not worried about a Fibonacci heap. How much could we spend on deletion without making this sum any bigger than it is right now? Right, suppose the cost of deletion was v, O of v. What would this term become? V squared, and it would disappear because it's the same as that. So we can spend as much as linear time on a deletion. On the other hand, how much can we spend on the insertion and be guaranteed not to blow our v squared budget here?
V squared.
No.
How big can E be?
V squared.
Yeah, E could be as big as v squared. So we'd love to have insert be constant time. So if we sort of make those our requirements, we hope we can do deletion in time O of v and insertion in time O of 1, then if we can create a priority queue like that, our entire algorithm is linear now on a adjacency matrix. Okay? So we'll see if we can do that. And what about if we're using adjacency list? So it becomes this picture. And what would it take
What would we want constant in that case?
if we could get constant time deletion and constant time insertion? Then we would have O of v plus v. Let me pose this question to you. Is that theoretically possible? To have a priority queue that has constant time insertion and constant time deletion? Yeah?
I think you could sort of list in n time that you just put it in the priority queue and took it out. And there's a minimum, we have a minimum time of n log n.
Well, okay, so if you're thinking of using a binary heap, there would be that log v term. Let me repose the question. It's not theoretically possible. Why not? Yeah.
You have to find the minimum, so you still have to iterate over all the elements.
Well, he's saying you have to iterate over all the elements, but that's not, for a binary heap, that's not true. You only end up looking at some of the elements, yeah?
You either have to, okay, so if you're using a binary heap, you have to find the position for that element, which is not constant time. For an insert.
Okay, so the problem with these arguments is they all sort of start, you're making assumptions about how the heap will be represented. Maybe there's some fancy data structure you don't know about. Turns out there's not. What's a definitive proof? How can we prove something's impossible? Yeah?
So what would the decision tree look like in this case to find the minimum?
Okay, so he's bringing up the idea of a decision tree, which is the right track, but we don't even have to think about decision trees. One way to prove something is impossible is to show that if you could do it, you could do something else that's known to be impossible. Okay? What's one thing that we know is impossible? It's the only thing we've proven. Yeah? Let me get your idea.
Was it that for comparison-based algorithms, it can only be log n at the shortest time?
Okay, what we showed is that for comparison-based, that it was impossible to have a comparison-based sorting algorithm with a worst case better than n log n. Okay, how does that help us here? We're trying to prove it's impossible to build a priority queue. This is a comparison-based priority queue with constant time delete and constant time insert. What could we do if it were possible to build such a thing? Yeah.
I mean, it has to be sorted in order to like...
Well, you don't have to assume it's sorted. Yeah?
If that was the case, we could build a heap sort that would run in real
Exactly.
time.
So heap sort would take linear time, would be O of n, if you could have a constant time. Both these operators are constant time, because all you would do is, you got n elements, you throw them all into a priority queue. That would take linear time. And then you remove them in order. That takes linear time. And now you've sorted them.
So we have a comparison-based sort that runs in linear time.
So what we've said is, if you could do a constant time delete and a constant time insert, you could do the impossible. Which you can't. Therefore, you can't do constant time delete and insert. So we can't wish for that. So what's something we can say about delete and insert? We want to keep the total complexity to a minimum. Okay?
It's better to have the delete be the cheaper one or the more expensive one than the insert.
Is it better to have delete be cheaper than insert? Keep in mind that with adjacency list, you're typically dealing with sparse graphs. And the sparse graph, E and V are the same roughly. So to keep this at a minimum, we want these two to be the same, right? We wouldn't want to make this constant and that V because you end up with a V squared term over here. And vice versa. So let's just wish that they were, ideally they'd be constant. They can't be. We want them to be small and the same in order to balance things out. So let's just wish that they're all log V. If we can find a way to do deletion and insertion in log V time, then we're okay. And then we have E plus V log V. So not linear. Can't have linear. That's theoretically impossible. Okay. Now Anthony mentioned something called a Fibonacci heap. We won't look at it, but it actually could go a little bit better than E plus V log V if you use a Fibonacci heap. We won't go there. We'll just look for ways to achieve these two goals. Okay. Any questions I can answer at this point before we dive into priority queues? Yeah.
Why did you say that if one was constant and the other one was linear, that it would be V squared, because isn't it addition?
Well, if delete took linear time and insert took constant time, we end up with O of V squared plus O of E plus O of E plus V. So we end up with O of V squared. That's not a good trade-off. And if we had this be constant and that linear, we end up with O of E times V, which is at least as bad as V squared. You have a question?
Well, earlier you mentioned that if we could have a linear time for both, or a constant time for delete and insert, we could have a linear times comparison sort.
Mm-hmm.
But we know these are weights and they're probably integers. Does that mean we could probably use like like something like radix sort and just pull it apart and speed it up?
Yeah, right. So what he's asking about is what I've described, what I'm talking about here is a comparison-based priority queue. Just like you can have non-comparison-based sorting algorithms that are faster than in log n, you could build a comparison-based sorting algorithm. I mean a non-comparison-based priority queue. We'll just stick with comparison-based. Okay, so here's a way to do the first thing, where we're going to have our goal is to have constant time insert, linear time delete min. So let's see how that would work. So to create a party queue, we just create an empty array with an index for each vertex. We can keep track of whether it's empty or not. Then we got the insert or change operation and the delete min operation. So if we want insert or change to be fast, how would we do it? Notice, what are we storing in the array here? So this is saying that A is on the priority queue with a weight of 2. B is on the priority queue with a weight of 5. C and D are not in the priority queue. E is with a weight of 3. So these are the weights of the things that are in the priority queue, or it tells you what's not in the priority queue. So what's it take to do an insert operation? Let's say we want to insert F if it's not there, or change its weight if it is. Yeah?
Well, if you stored it as an array like this, with an unordered array, then an insert would be constant,
Yeah.
and delete would be.
Right, so if we got to insert or change F, you just change it. F is an index into the array, or if our vertex names aren't integers, small integers, we got this is a hash map instead of an array. But anyway, we go straight to our F and store it and change it to a 4. Great. Now, what will happen when we insert or change B? We go right here, change it to 1. So it's fast to do that. That's what we wanted. We wanted fast insert. We're willing to have a fast insert at the cost of a slow delete, because we do more inserts than we do deletes. Right. Now, what's it take to do a delete min?
Linear, so sweep through.
Got to sweep through and find the smallest weight. So we find the 1, it's there. And so we pull it out and report here's B is the minimum. Insert or change H to 3, we just go change it. Another delete min, we just sweep through, we find that one. And that's that. That's very simple priority queue. Yeah.
For delete min, could we use something, or why can't we use something like select, or quick select, to find the smallest in?
Okay, so now you want to improve. Okay. Okay, quick select. Okay, so what does quick select take as a parameter?
Index.
Right, so we're trying to find what will be stored at a particular index if the array were sorted. Okay, so really what we're interested in is what will be stored at index 0 if the array were sorted.
Right.
Okay, so what's the complexity of quick select?
Log n.
No. Yeah, it's like, it's in log n in the worst. Well, it's in log n in the average case. It could be as bad as n squared. So it wouldn't help us here, get below n here. Basically, we got to find the minimum element in an array. But that's fine. We're willing to spend a linear amount of time. Right? So having done that, what's the complexity of creating a priority queue? Okay, that should be O of V.
Is the slash infinity?
Yeah, the slash is null, or infinity, I guess. Not there is what it means. Okay? To insert, it's constant time. To test, it's empty. Oh, yeah, that should be constant time as well. And delete min. So these should both be O of V, and that should be 1. So here's my typos. So that we met the goal that we wanted. Now, for the adjacency list, we wanted insert and delete to be both log in. And we can achieve that with a binary heap. So I suspect you've seen binary heaps before, so let's just review. A binary heap is, first of all, a complete binary tree. It's represented with a complete binary tree. What's a complete binary tree? Yeah.
Every level has all the possible nodes as you go down, and the very last level might not.
Okay, so every level except the last is guaranteed to have the maximum number of levels. So you got 1 at the root level, 2 at the next level, but then only 3 at the bottom level. But there's one more thing we need to have to make it complete. Yeah?
Wasn't it that on the left side of the branch, you have to have those?
Well, that's what makes it a binary heap. But what makes it complete? What also has to be true of the shape of the tree. Yeah?
Does the left side have to be filled from the right side?
Right. Any holes have to be all the way to the right. So when you fill the bottom level, you start from the left and fill in left to right. So that's what complete is. Okay, we're assuming that the vertices contain elements that can be compared. So it's comparison based. A child's element is no smaller than its parent. So a child is no smaller than its parent. Which means what? Where's the smallest element in the binary heap? At the root. This is not a binary search tree. Binary search trees aren't complete are guaranteed to be complete for starters. And they use a different ordering. Okay? But in each case, any node is going to be less than or equal to anything underneath it. So 5 is less than or equal to the 6 or the 8. 3 is less than or equal to 9, and so on. Okay? To insert, you just stick it in the next spot of the tree, and then move it toward the root as far as it'll go. So let's suppose we want to insert 1. Where's the next spot in the tree?
Right at 3.
It's right there. And then we gotta compare it to its parent, and if it's out of order, we need to swap them. So are they out of order?
Yes.
Yeah, so we swap them. And you keep doing that to either reach the root or you find something that's smaller. Okay, what about those two?
Yes.
So we swap. Okay, so that's an insertion. Here's another one. So why did I put it there instead of somewhere else? Right, that's just the first. The other level is full, and we want to put all the way to the left here. So we do that. We compare the 4 and the 6. We push it up. We compare the 4 to the 5. We do a swap. We compare the 4 and the 1. 1 is smaller, so we do nothing. Yeah. So that's the insertion operation of a priority queue. So if you
I thought I saw something changing on the far right. On that far right now when you were doing the animation. That probably was intentional.
Oh, yeah.
Oh, good.
Yeah.
that's an animation bug as well. Try to keep track of these. Maybe someone can remind me. What's the complexity of this? Suppose you have n elements in your priority queue.
In the worst case, or?
What's the worst case complexity? The insertion into a priority size n. Yeah? It's log n. So what's your reasoning?
So because it's binary, like the height is going to be the worst case scenario, you start at the bottom and go all the way to the top.
Okay. So she said since it's a binary tree, its height's going to be log n. Actually, you can't just say because it's a binary tree, its height is log
Because
n.
it's a balance.
Because it's a complete binary tree, its height is log n. And the worst you can do is start at the bottom and push it up to the top, and there's only log n levels. So the work you do is proportional to log n in the worst case. Okay. Now at this point, someone usually asks a particular question. Well, I will ask it. How did you figure out where to put the 4 in the first place? You have to, if you have to look at every vertex in the tree to find the first open spot, that'll blow our budget completely. We don't have to look at every vertex. Yeah?
You implement it as an array and you dump it at the end.
Right. In reality, you don't use a linked structure like this. You put it in an array. So we'll come to that. Now, what about deletion? So what we got to do is remove the element that we're trying to delete. We want to get rid of the 1. Now, once we shrink this tree by 1 element, we're not going to need this node right there anymore, because we got to maintain completeness. So what we do is we take that 6 out and throw it up there. Right? Throw it up there. So we got the 1 out. That's guaranteed to be the minimum. We don't want to have, we can't have the hole at the top, so we take out the last element at the bottom. And now we just got to fix up the tree. So what's involving, what we have to do to fix up this tree that has 6 at the root? Yeah.
Replace it with the minimum of its children.
Right, you take the minimum of the children and swap that with the root. So the 6 and the 2 will change places. And we just continue doing that down the tree. 6 and the 3, you swap them. And now we're done. So here's another root now. What will happen here? The 2 comes out, and that's what we give back. But we swap them. No, we don't swap them. We take out that last vertex and we put its value up there. And then we rebalance like before. What's the complexity of that?
Log in.
Yeah, that's just log in again, because the worst that can happen is you push something all the way down to the fringe. And again, the height is log in. Yeah.
Isn't the average case for insertion constant, though? Or
No. I don't believe the average case would be constant. Okay. The problem is we had an insert operation, but we need an insert or update operation. So what's missing from my picture, first of all, are the keys. We just have the weights here, but typically there'd be a key, A, B, C, D, a vertex key associated with each one. What if we have to go find the weight for vertex V, for vertex B, and change it? How do we do that? Yeah?
Breadth first search.
Well, breadth first search, sure, but what's the problem?
For an array.
For an array.
Yeah, that'll take linear time. We can't afford a breadth first search. We can potentially have to look at every node to do that. We can't afford that. So we need a way to find a particular vertex in constant time so that we can change it. Yeah?
we use a dictionary?
We could use, basically we need an auxiliary array or an auxiliary dictionary hash map or something like that. But we can fix that up too when we move from this representation to an array representation. Okay. So now I've annotated my tree with vertex names. So we can now see that the root vertex has a weight of 1, and that's B's weight. And the next vertex has a weight of 4, and that's A's weight. So we got the full information in there. And I claim we can take that information and store it in an array like this. Okay. How does that happen? How does that work? How can you encode a binary tree into an array? Yeah?
We do it because we know that each level is complete, and we know that each level grows by powers of 2.
Okay. So it's complete. So you notice the B. Trying to figure out what I'm looking at now. Yeah.
Instead of doing an array of things, do it as an array of structs, right?
Yeah. All right. Rather than try to stand here and think if I made another typo, let's.
I think your array is showing what would happen if you removed B and then fixed the E.
Yeah, but they're not supposed to show that right now.
No, yeah. On that.
Yeah. Okay, that's just a straight. Okay, that's better. I have a slide I should have deleted. Thanks for helping me there. So I was getting ahead of myself.
Now it makes sense.
Yeah, now it makes sense. But rather than try to explain this right now, let's take a break and I'll explain it afterwards. In the meantime, I'll delete that road slide. So the correspondence there, the root up there is 1, a weight of 1, vertex B, and it's here. And we fill it in like that. Since it's complete, it just fills in nicely from left to right. There's the top level, here's the next level, here's the 4 elements on the 3rd level, and that's the only element on the 4th level. Now, up there, it's easy to go from a parent to its child or back, because you're just following references. How do you do it here? Yeah?
So because each level is twice as big as the next, in the array, a node's children is at 2 times that index, and 2 times plus 1.
Okay. So for example, this C right here, it's an index 3. So 2 times 3 is 6, that's one child. 2 times 3 plus 1 is 7, that's the other child. That works. I made it 1-based indexing to make that work better. If it's 0-based, it's just a small adjustment. How do you go back? Yeah?
Integer divide by 2.
Yeah, you do an integer division. So the parent of this one here, divide by 5, you get 2. I mean, divide by 2, you get 2. So it's there. Okay? So it's easy navigating around. Great. We don't have to waste, we don't have to use dynamic memory. Why don't we do this for binary search trees? Yeah?
Because of all the empty spots you could possibly have.
Because of all the empty spots. So it turns out that you can have an n-element binary stick that require 2 to the n nodes, a 2 to the n length array to store. So like a 30-element binary search tree that had a 1 billion element array to store it, most of which are blank spaces. You have to leave the blank spaces in order to make the index computations work. So it works nicely for a heap, binary heap. So that's summarizing what we just said. And tree manipulations are converted into array manipulations. Now, we've got to be able to quickly find, let's say we want to change the weight of 3. Of E, rather. We want to change the weight of E. So we have to be able to quickly find E is here and change its weight. So what we can add is a second array that stores, since indexed by vertex name, and it contains the index in that array where that vertex is stored. So if we want to find E, it's at index 4. If we want to find F, it's at index 5. So that's what makes that way we can quickly go find what we're looking for. So let's do a delete min, and I'll highlight in both the tree and in the data structure right here. So the first thing in delete min is you've got to identify the first and last elements. And that's easy to do in an array. You can see what the first and last are. Then we get rid of this one and we stick the 6G in its place. But when I do that, we have to update down here. So what changed down here when I did that? Yeah.
B's no longer in the array.
So B disappears from this. Okay. And what else changes?
G becomes 1.
Right. G index was 8. Now it's 1. So every time you move something up there or remove something up there, you've got to do the same thing down here. Okay. Now we compare the root with the 2 children under it. That's what it turns into here. We have to swap the C and the G. So when we do that, we swap them there. We're going to be changing down here as well because the indexes are changing. So you'll see something change down here. Now we do that comparison. And again, there's a swap, and you'll see a change down here as well. Okay. So that's a delete min. Now what if we want to change the weight of E to 3? Where do we start? This is, okay. Right, we go to index E. We see it has a 4. That tells us E is stored at index 4 up there. And we want to change it to a 3. So we change it to a 3. And then what do? We got to try to push it up. So we compare it to its parent. It's smaller. We swap them, and so things will change down here. We compare it to its parent, and we stop where we are. So we got this nice, now we can forget about the binary tree. This is our representation, just a couple of arrays. Yeah?
Would you have to check the children too, though?
Okay.
Because if you swapped it, or if you changed E, say this is what we had, you changed E to 6.
So if you make the weight up, if the new weight is smaller than the old weight, you've got to push it toward the root.
So you check that first.
If it's larger than the old weight, push it toward the leaves. Now this might be a good place to mention that next week's caddis problem will involve Dijkstra's algorithm. And there are programming languages, like Java for example, has a priority queue built in. But the priority queue that Java has does not provide an efficient update operation. It provides an update operation, but it requires linear time. Okay? Be sure you read the description inside of Canvas, because I give you a way to work around that. If you just blindly assume it's going to be efficient, you might run out of time in your algorithm.
Do we need a decrease key operation? Like, can we just keep adding duplicates in the queue and realize that they've been duplicated?
Yeah, well, that's the optimization. I'll let everybody else read about it. Okay, so as I mentioned before, and as you've probably seen before, you can sort using a binary heap. Basically, first step is you throw everything into the heap, and then you start doing delete mins, and they'll come out in order, and you can. It's just an efficient way to sort. It's an n log n way to sort using a binary heap. And what's nice is that when your binary heap is full, you got an array full of things. Now, typically for heap sort, you do a max heap, not a min heap. What would happen when you did the first delete max? Yeah?
Create a spot at the end of the array.
It creates an empty spot at the end of the array. That's where you can put the max element, right at the end of the array where it belongs in the sorted one. And so what happens is the heap shrinks, the sorted part grows, and when you're done, it's sorted. It's very efficient in terms of space, but I'm not going to talk about that any more than I just did. Okay, so that sort of finishes our look at shortest paths algorithm. And it took a detour to talk about alternatives for priority queues to make the algorithm efficient in a couple of cases. Any last questions I could answer before I move on? Yeah?
Is heap sort better than a quick sort?
Well, he asked, is heap sort better than quick sort? Heap sort's better in the worst case, but it's slower in the average case. Yeah?
Does it also take more memory?
Heap sort.
No.
Because you have to initially represent the nodes.
No. It doesn't take, it just takes the array you start with. You take the array you start with, you turn it, in place you can turn it into a binary heap, and then in place you can turn it into a sorted array. In fact, if you have the n elements you're going to turn into a heap all at once, you can convert it into a heap in linear time. If you get them one at a time, the best you can do is n log n. All right. Well, we're going to change gears completely now. And we're going to go back to chapter 1. And we skipped over chapter 1, so we've done 0, 2, 3, 4, now back to 1. It's 1's turn. And chapter 1 is about number theory. And the reason we're studying number theory, by that I mean things like greatest common divisors, prime numbers, exponentiation involving large, modular exponentiation involving large numbers, is those are going to be the raw pieces we use to make public key encryption. So our goal as we go through chapter 1 is to gradually work our way up to understanding how public key encryption works. But first we got to look at some basic algorithms on numbers, on integers, on arbitrarily long integers. And essentially throughout we'll be dealing with modular arithmetic. And so if you are unsure about what modular arithmetic is, or have trouble quickly doing modular computations, it's going to be a struggle. So you need to get really good at it. So let's just talk about it. So when I say x mod n, where x and n are both greater than 1, what does that mean? What does it mean when I say like 7 mod 3? Okay, I'll take your answer.
When you divide x by n.
Okay, so he said it's the remainder when you divide x by n. That's one way of looking at it. Think of another way of looking at it. Right, so 8 mod 3, you divide 8 by 3, you get a remainder of 2. So that's the modulus. Okay, well, let's see. There's one property it's good to know. What does that tell you?
It's not unique.
Yeah. So what is that saying to you? Yes?
So two numbers can be different by a multiple of n. And
Okay.
considered equivalent.
So, yeah, so what this is saying is that x mod n can be thought of as x plus k times n for some k. So if x is 8 and n is 3, and so x mod, 8 mod 3 is 2, what k are we talking about?
Zero sum.
What k will make x plus kn equal to? Yeah.
Zero,
Uh,
right?
No.
Because your remainder is 0. And then
X mod n is, if x is 8 and n is 3, x mod 3 is 2. 2 is not equal to 8 plus 0 times n.
8 plus -2.
Negative 2 in that case. Okay. So these are all different ways you can think about it. Try to get the right intuition. Okay, so 4 mod 5, that's just 4 plus 0 times 5, which is 4. What about 14 mod 8?
6 plus 8 times -1.
Okay, so that fits our pattern. 101 mod 4. I mean, the important thing isn't to come up with the k necessarily, it's just to be able to say quickly what it is.
1.
Yeah, it's 1.
So 25 times 4.
So basically, the way I look at it is I don't try to do division. I just say, okay, how much bigger is this than some multiple of 4? And I think, let's see, 4 is, 100 is a multiple of 4, so I'll subtract 100 from the 1 and 1 and I get 1. So I think about multiples of the modulus. Okay? What is negative 14 mod 8?
That's 6. But do we have rules? Because, like, do the quotient have to be the same sign as the...
Well, I got a rule right up there.
So we don't have to come up with a unique solution.
So, what is negative 14 mod 8? Yeah. Okay, so she's saying 2.
2 minus 2 times 8.
Who thinks it's 2?
It is.
Who thinks it's something different?
Ah.
Okay, well, let's see. Okay, so we can write this as negative 14 plus 2 times 8 and get 2. So another way to think about mod is you either add, so if you're taking negative 14 mod 8, you either repeatedly add 8 until you get a number in the right range, or you repeatedly subtract 8 until you get a number in the right range. So we take negative 14 and we add 8, that's negative 6. We add 8 again, that's 2. There's the modulus. Yeah?
There is a formal definition of the mod operator that gives you in that range.
Well, right there.
Well, in terms of the floor function.
In terms of,
Of the floor function. So x mod y is x minus y times the floor of x plus y.
okay. I'm not dealing with, I don't have to say anything about the floor operation or use floating point arithmetic or anything, real numbers. We can work with it from there. Yeah?
Is there any way to find out what k is without knowing what the x mod n is?
Well, as he just said, you can do a computation using the floor operation, do real division. I mean, yeah, there are various ways. I want you to be able to quickly do it for reasonable size numbers. I want you to be able to look at this and say, okay, negative 14 mod 8, okay, if I add a multiple, you want to add a multiple of 8 or subtract, or you want to add a multiple of 8 to that brings it into the range 0 to 7. So I look at that and say, I'll add 16, that gives me 2. Now, the problem with this is, well, what's negative 101 mod 4?
could be 3.
Yep.
It's gonna be 3.
Yeah, so it's 3.
It's-
How do we know that? Yeah,
104 is a multiple of 4.
Yeah.
By adding that, you get it into the
Right.
range 0 to 3.
yeah. You add 104 to that, you get 3. 104 is a multiple of 4. Add to that, you get 3.
So in this case, the remainder has to always be positive.
Yeah, typically when we ask for the modulus of something, we want a number between, say, from 0 up to, but not including the modulus. So for this, I want a number between 0 and 3 for that answer. Now, Java and C do this inconsistently. For negative numbers, they basically, to take the modulus of a negative number, they negate the negative number and then take the modulus. So they get it wrong. Okay? They would say that this modulus is -1.
Is that C or Java?
Java and C. So they would take -101 mod 4. What they do is negate this, take 101 mod 4, and then negate the answer. So 101 mod 4 is 1. Negate that, you get -1. Now that's not so bad. Yeah.
Could you just add the answer they gave you to whatever number you're modding by, and then there you get
Yeah.
the real answer?
So -1, if you add a 4 to that, you get the 3 back. Yeah.
Is there a reason why they do it that way and not the actual negative?
Yeah, I don't know exactly why they do it that way, but I want you to know that, here when I say modulus, when we're applying the mod operator, I want a number between 0 and the modulus, not including the modulus. Yeah, we'll use this, yeah. Oh, go ahead.
I'm a visual learner, and for anybody else, a really good example of doing mod is if you have a clock and the number of hours, like let's say you're modding my clock, so 12 hours in a day, and if you have a row of like 14, if you're going positive, you wrap around that way and see the commands. If you're going negative, the length is the same, but you wrap around to the left.
Okay. So yeah, modulus occurs a lot of places. Where does modulus, think about int representations. Int representations in, say, Java, they're 32-bit numbers, and so it's basically integers mod 2 to the 32. Where a number gets too big, it wraps back around. Okay. Clocks work mod 12. Car odometers used to work mod 100,000. You get 100,000 miles, it roll over to 0. Nowadays, I don't know what happens. Maybe mod 1,000,000, it may just keep going forever. No one knows. All right, so sometimes we use this notation. X and Y are equivalent mod n. So what's it mean for two numbers to be equivalent mod n? We've got 3 definitions up there. So, yeah.
The X mod n is the same number as Y mod n.
Yeah, X mod n is the same as Y mod n. So 5 and 9 are both equivalent mod 4. Because 5 mod 4 is 1, 9 mod 4 is 1. Okay? They're also equivalent if the modulus evenly divides the difference. So what's 9 minus 5? 4. And and 4 evenly divides that. So 9 and 5 are equal, are equivalent mod 4. So if the two numbers differ by a multiple of the modulus, they're equivalent mod 4. So various ways to think about it. So is that true or not? Are 5 and 12 equivalent mod 7?
Yes.
Sure. 14 and 36, are they equivalent mod 3?
No.
It's a quick way to see it.
Prime factorization.
36 is divisible by 3, but 14 is not.
That's what I noticed. 36 is a multiple of 3, 14 isn't, so they can't be equivalent. Mod 3.
Yes.
Okay.
Yes.
Okay, how do you know that quickly?
They're both even.
They're both even, so divided by 2, you're going to get no remainder. So they're both 0 in mod 2. Yeah. Whenever you see something like this, there's typically some trick. I'm not expecting you to do the division in your, well, I guess I am in a sense expecting you to do the division in your head. Except you don't care about the quotient, you just care about the remainder. about that?
No.
Are they equivalent mod 10? Well, we know that if we do a division by 10, we're going to get just the last digit as the modulus, and the last digits are different. So that's similar to the previous example. Okay, so here are some properties of modular arithmetic. So, what does that mean? So it's saying if x and x prime are equivalent mod n, and y prime are equivalent mod n, then x plus y is the same thing as x prime plus y prime mod n. So if you're doing modular arithmetic, you know when you're doing arithmetic, you can substitute equals for equals, right? Well, this is just saying that that property applies in modular arithmetic, but when we're saying substitute equals for equals, we mean you can substitute things that are equivalent mod n. So you can replace equivalence with equivalence. So for example, what'd be a quick way to do 14 times 25 mod 4?
Take the mod.
Remember, you can replace equivalence with equivalence. So what are you saying?
Take the mod of both.
Take the mod of both.
And then multiply the mods.
And then multiply. So we can replace anything that's equivalent. We can replace 14 with anything equivalent to 14 mod 4. Okay? So 14 mod 4 is 2. So we get 2 times 25 mod 4 is 1. So we get 2 times 1 mod 4, which is 2. So you can use the modulus to beat these numbers down to smaller values. Okay? What about that? 2 to the 345th power mod 31. So what am I trying to get you to see here?
31 or 32?
31 is 2, like base 2 to an exponent.
What was that?
You're checking, like, if you look at 31, you want to see if you can put it into base 2 notation.
Okay, so yeah, mod 31 is suspiciously 1 less than a power of 2, right? So here's the idea. I'll just regroup it. This is just 2 to the 5th to the 69th power. Okay? This third rule up here says that I can replace what's in here with anything that's equal to that, that's equivalent to that, mod 31. Right? I can't do that trick with the exponent, but I can do the trick with the base. Well, what's 2 to the 5th? Mod 31. Right, so replace equivalence with equivalence. I get 1 to the 69th mod 31. We can do that in our head. It's just 1. Okay? So that's a nice thing about modular arithmetic, is that you can use it to, if you've got a massive operation, mod something, you can just beat on the operands and make them smaller and things can come out. Okay? Modular arithmetic is also commutative and associative, like you'd expect, and distributive. So you've got the usual rules. All right, we'll stop there, and next time we'll build on this stuff.